So oftentimes when I'm flying out these RPO missions and I learn something new or non-intuitive about more efficient paths to take or more efficient burn profiles, I often find myself with that nagging question of, is that really the best that I could do? And so in this lesson, I'm going to show you another example of how I use iterative modeling to try to take those things that you learn sort of through experience and turn those into some sort of truth via analysis. So I already kind of did a more in-depth video about STK Analyzer in my ISS video over a year ago. So if you really want to see the buttonology, then you can kind of go and check that video out. But I'm really just going to show you kind of another use case for how I think iterative modeling can teach you non-intuitive things about the motion of objects in space. So just really quick scenario design. We have this flyer satellite that's basically going to burn with its 10 Newton thruster for 1 hour, and then we're going to record the distance. So the 10 Newton thruster is just modeling specs off of one of these really common 10 Newton thrusters that are on orbit with all these different satellites. And what we're going to look at with STK Analyzer is if I were to burn in any azimuth and then wait a certain amount of time and then record my range from the original reference point, what's the furthest that I'll go in 24 hours, regardless of the direction of burn that I choose? And what's the furthest that I'll go at 9 hours, 8 hours, 10 hours, etc.? And which of the burn azimuths is the most successful? So that's kind of the experiment design. So we kind of have two variables that we're going to look at. One is the azimuth of the burn. I'm just going to do from 0 to 90 because I'm assuming that there's some symmetry between negative radial and negative in-track and in-track. So if I just do positive radial and positive in-track, kind of this quadrant of burn directions here, I'm pretty sure I can make all of the same conclusions. And spoiler alert, in preparation for this video, I already did the azimuth in every single direction just to see that those conclusions were true. So similar to the last time we did Analyzer, you have to set up the variables. So here I've got the azimuth is the first variable, and then this propagate that currently has a 1 second time, we'll just turn that to 0 seconds, is going to be the other variable. So we're just going to let this change every hour and then record the range from that reference point, basically the center of the screen at the hour mark. So we'll take it at this 0 point. So here you can see it's just modeling a pure radial burn. Here's how far I got in an hour, 43.73 kilometers. And then we'll take it at 1 hour, 2 hour, 3 hour, etc. So you can see after 24 hours, obviously because it's a pure radial burn, I just made it NMC, so my range won't be very far. So I'm assuming radial burns will not be the solution for the most distance that I can go. But there is a solution, and the STK Analyzer will iteratively go through each of the different options until it finds the best option. So let's just go ahead and launch in. So just go to satellite plugins, STK Analyzer, and we'll set up our scenario. So here's the first screen that you see in Analyzer, and you can see I've got the trip, the azimuth, and the range already selected. So 2 inputs and 1 output. We're going to use a design of experiments because that gives you really the most options for how you manipulate the variables. So we'll just go ahead and throw this in. Do a parameter scan because, again, I feel like that's the easiest to intuitively understand. For trip, we'll let it go between 0 and 86,400 seconds because it's in seconds. And then we'll have 25 different levels there, 0 being the first, and then at each hour, it'll check the other 24. And then for azimuth, we'll go from 0 to 90, and again, we'll have 91 levels there, so that does 0, 1, 2, 3, etc. Okay, so here's all the data. You can see the time is listed over here, and then the direction of the burn was listed over here. So this is showing all of the pure in-track burns, and then recording the kilometer range that we got over 0, 1 hour, etc. So the first thing we're going to answer is the riddle, when is 21 greater than 24? So something non-intuitive that we can get from the data right away is what was the furthest that we were able to get, and what was the time and azimuth that built the furthest distance. So let's just sort this by descending values, and you can see that at 21 hours, which is what this is in seconds, and 88 degrees azimuth, this is when we actually got the furthest. So if we go and look at this in the 3D graphics window, this is going to make total sense, but at my first gut instinct of, well, why wasn't there a azimuth that would get me further in 22 hours or 23 hours? To me, this is kind of a non-intuitive result. Regardless of direction of burn we choose, the furthest that we can get from our target reference is at the 21-hour mark, and then any of the options that we choose will bring us closer back to the target. So let's just go and model it and then take a look and see if we can understand why. So we got 88 degrees azimuth, and we've got 21 hours. So boom, there it is. And from this, to me, it's totally obvious why this was the occurrence. Because regardless of direction you choose, we know that in-track is going to be the most successful because the semi-major axis change is really going to create drift away from your target area. But semi-major axis has this interesting thing where because you're changing the eccentricity, when you are approaching your perigee point, you start to drift back to your original target location. And so regardless of the burn that we choose, because in-track is the most successful to move far, some measure of in-track burns is going to produce this back eastward motion regardless of the direction you choose, so that at the 24-hour mark, you will actually be closer to your target than you will at the 21-hour mark. Totally makes sense when you look at this screen, but it's still something that I think was originally non-intuitive to me when I first saw this is the results. So cool, just looking at the matrix like Excel style chart, you can already draw some interesting conclusions. Let's throw some graphs on there and then try to dial in some more conclusions. So before I blow your minds in 3D, let's take a look at the 2D window. So right away, already I can see some more conclusions just from this graph. What you're seeing here is as you move across in time, it's more hours that we're waiting, and as you move up in the y-axis, it's further range that we got. So here you can kind of see that shape that shows that around 21 hours is the peak, and then you start to decrease down as you get to waiting longer. Okay, so we already got that from the matrix. What's some other interesting stuff? Well, look at the spread of the data and how it opens up like a cornucopia as you move longer in time. What this means is that if you just look at right after the burn ends, it's irrelevant, pretty much, the direction of burn that you choose. Each one produces the same relative distance. But as you wait longer and longer, the difference between the different azimuths that you choose produces a greater and greater spread of data. So each one of these time slices is 90 different data points. You can see the data points spread greater and greater. So that's first conclusion. The direction of the burn matters depending on how long you want to wait. The next conclusion that we can draw is you can see that this is not a straight line, like a linear relationship, meaning you wait 1 hour, you move twice as far, you wait 2 hours, you move 3 times as far, you wait 4 hours, etc. There's actually this greater than linear relationship where if we wait 24, we're not moving 24 times 43, we're moving 24 times 265. So next conclusion, if you want to create greater distance, give yourself more time. All right, so let's look at the impact of azimuth and what that means. So I'm just going to color these according to azimuth. All right, so the next conclusion here is that you can't just take one azimuth and always produce the greatest range depending on which time slice you care the most about. We'll see this more in the 3D graphics window, so I won't deep dive into it, but basically you can see that red, which is the most successful up here, regardless of what that azimuth is, and we know it to be approximately the in-track direction, is actually the least successful when you're talking about short durations. Whereas purple, which looks like it was the king of this short duration, eventually becomes, the bottom. So that's probably something like a pure radial burn, because we can see this is the one that in 24 hours basically moved no distance. And one final conclusion that you can get just from this graph is there's actually a minimum distance that you can go based on how you choose your burn. Kind of conceptually, there's no burn that if I burned in a particular direction, I would go back to my original starting location in 6 hours. The only way to get back to my original starting location if I expend delta V is really those pure radial burns that produce NFCs. You can see at the 12-hour point is basically the peak minimum distance. Regardless of the burn direction that you choose, you cannot go any closer to your original starting location than 1,328 kilometers. All right, sweet. Let's get really cool. Let's turn this into 3D. Sweet. So here's that same graph. You can see basically we're looking across this way is the trip, and up on the y-axis is going to be the range. But now we have the ability to move around and see the impact of azimuth. We can zoom and fly around in the space of these data points and select one and try to see if that meets exactly what we're looking for. So I'm just going to color this up so we can get some more usable data. So let's go ahead and color and size by range. And then let's take a look in the azimuth direction and see if we can draw anything interesting conclusion-wise from this. All right, so it's a little bit hard to make out all the data. So what I'm going to do is I'm going to shade off the back half of the trip times because of the loopback effect of radial burns. You're getting all these overlapping points, and it's hard for us to really pull out the information that I'm kind of looking for. So let's just downscope down to something like 12 hours. Cool, so now this is where I can start to draw some interesting conclusions. It's somewhat difficult to see based on the resolution right now, but you can see that there's basically this slope upward for really short travel times, meaning that an in-track burn, which is the ones that are represented on the far left, moves slightly less distance than a pure radial burn does. So if you're really concerned about being further in a short duration of time, you want to be more to the radial side. And then you can kind of see how this has this bow shape where it kind of peaks in the middle. So if you have sort of a middle hours of time, say right around the 7-hour point, then it's actually best for you if you want to create a larger distance to have approximately equal in-track and radial direction for that burn. And then slowly and slowly it shifts more and more to in-track until you get to that 88-degree 21-hour mark. But again, we get another conclusion, another way to represent the data that based on the amount of time you want to wait, there is a relationship between the direction you choose and the optimal way that you could do that. So this is just kind of the ways I like to use iterative modeling to start to find these really unique cases and build a better understanding about how objects in space move. A lot of it's very intuitive, but using the modeling software gives you the opportunity to have that supreme confidence that what you're learning is actually being represented